Welcome to a walkthrough of 5 queries executed against the multi-agent orchestrator in flow.py. For each query, we will play back the captured log so you can see exactly how the planner, researcher, distiller, and formatter agents collaborate to produce the final answer. Query 1. A simple greeting, hello. The orchestrator spins up a planner node, which decides only a formatter is needed. Total wall clock, 28 seconds. Final answer, hello, how can I help you today? Query 2. Fetch the Wikipedia page on Claude Shannon and extract his birth date, death date, and 3 key contributions to information theory. The planner dispatches a researcher to call the fetch tool over the gateway, and finally a formatter. The final answer correctly returns April 30, 1916, and February 24, 2001, along with 3 contributions. Query 3. Find the populations of London, Paris, and Berlin, and identify the 2 closest in size. The planner fans out into 3 parallel researcher nodes, 1 per city, and a formatter merges the results. The final answer reports London at 9.09 million, Berlin at 3.69 million, and Paris at 2.05 million, with Berlin and Paris the 2 closest in size by administrative city limits. Query 4. Read a path that does not exist. The planner recognizes that no tool can satisfy the request and dispatches only a formatter, which politely reports that the file at /nonexistent/path.txt cannot be read because the path does not exist. Query 5. For Lagos, Cairo, and Kinshasa, find current populations and growth rates and tell me which is growing fastest. Again the planner fans out into 3 parallel researchers, 1 per city, and a formatter assembles the results into a table. The final answer puts Cairo at roughly 23 million, Kinshasa at 17.8 million, and Lagos at 17.2 million, and identifies Kinshasa as the fastest growing at about 4.4% per year. All 5 logs and this video live in the run_logs folder. This demo verifies one claim about the Session 8 orchestrator. When a user query contains independent subtasks, the planner must emit them as concurrent nodes, and the orchestrator's ready layer must run them in parallel. The wall clock of that layer should equal the slowest branch, not the sum of all branches. The query asks for 3 unrelated facts: the boiling point of water, the speed of light in vacuum, and the height of Mount Everest. None of these depend on the others, so the planner is expected to fan out into 3 sibling researcher nodes that feed a single formatter. Watch the live log. The planner emits the DAG in 3 seconds. Then 3 researcher nodes start at the same instant and complete at near identical times around 12, 28, and 32 seconds. If they were serial, the layer would take more than 70 seconds. Finally the formatter synthesizes the 3 answers. Here is the verdict. The red bar shows the serial bound, more than 72 seconds if the branches had run one after another. The yellow bar shows the parallel bound, 32 seconds, the slowest branch. The green bar shows the actual layer wall clock, 33 seconds. That is 1.03 times the slowest branch, dominated by the slowest branch with only a small asyncio scheduling overhead. Pass. Parallel fan-out is verified. We run the same query twice. In run A the distiller returns all 4 requested fields and the critic passes. In run B we poison the first distiller call by stripping 2 fields. The critic catches it, and the orchestrator splices in a recovery planner that produces a corrected answer. The query asks the agent to fetch Alan Turing's Wikipedia page and return a JSON record with exactly 4 fields. Because the distiller is marked critic true, the orchestrator auto-inserts a critic on every outgoing edge. The critic verifies one property: the distiller's output fields dictionary must contain every field name the user query enumerated. This is intra-prompt, so the critic needs no tools. Run A. No patch. We expect a clean pass on the first attempt. Planner emits the DAG. Researcher fetches. Distiller returns all 4 fields. Critic passes. Formatter writes the answer. Run B same query, but we patch the skill dispatch to strip 2 fields from the first distiller call only. The poison stripper fires. The critic sees only 2 of 4 fields and emits verdict fail. The recovery handler reads the failure report, schedules a recovery planner node, and points it at the failed distiller. The new branch runs researcher, a fresh distiller, critic, and formatter. This time all 4 fields are present, the critic passes, and we get a corrected final answer. Run A passed on the first try and finished in 5 nodes. Run B failed once, triggered a recovery, and finished in 10 nodes with the same correct answer. Same code, same gateway, same DAG shape. The critic plus recovery loop. Welcome to a walkthrough of the coder skill in the multi-agent orchestrator. The coder skill takes a question that requires real computation, emits a short Python program, and the orchestrator automatically routes that program to a sandbox executor that runs it in a sub-process. The downstream formatter then quotes the program's standard output back to the user. Here is the demo query. What is the sum of the first 67,432 prime numbers? This is a question a language model cannot answer reliably from text alone. Sieving tens of thousands of primes and summing them requires arithmetic, not recall. The planner is expected to delegate to the coder skill, which will write a small Python program using a sieve, and print the total. Watch the orchestrator. The planner emits a coder node. The coder emits Python source as a JSON string under the key code. The orchestrator's static internal successors wiring automatically queues a sandbox executor node on the coder's output. The sandbox runs the program in a fresh temporary directory with a 30-second wall clock cap, captures standard output, and returns the result. Finally, the formatter quotes that output back as the user-facing answer. And there is the final answer. The sum of the first 67,432 primes is 27,332,806,411. The point of this demonstration is the separation of concerns. The coder skill is just a prompt that produces Python. The sandbox executor is a tiny sub-process wrapper. The formatter does not need to do any arithmetic. The orchestrator wires the 3 together by configuration, not code. That is the contract. A new computational skill is 1 prompt file plus 1 YAML entry away. Welcome to a walkthrough of the new translator skill, added to the multi-agent orchestrator without changing a single line of orchestrator code. The skill is defined entirely by 1 entry in agentconfig.yaml and 1 prompt file. Here is the query we will run. Translate, quote, knowledge is power, but enthusiasm pulls the switch, end quote, into French, Spanish, and German. The planner is expected to fan out into 3 parallel translator nodes, 1 per language, followed by a formatter that assembles the final answer. Watch the orchestrator. The planner emits 4 nodes. 3 translator nodes run in parallel, each pinned to 1 target language by its metadata. The formatter then collects all 3 translations into the final user-facing reply. Notice that no recovery was needed and no critic was inserted. This is a clean, single-pass execution. And there is the final answer, with 3 faithful translations. The changes required were strictly 3, 1 new entry in agentconfig.yaml, 1 new prompt file at prompt/translator.md, and a 2-line addition to the planner prompt so it knows the new skill exists and how to fan it out. The orchestrator, the skill registry, the recovery loop, and the gateway were not modified. This is exactly what a data-driven skill catalog is supposed to feel like.